In India, Prestress concrete has been there even before independence. There has been during the British time, they were used in the army. And then after the independence, a major project was undertaken to connect the northeastern part of our country, Assam Rail Link project, where substantial amount of Prestress concrete was used. Among the bridges, this is a bridge which is close to the place where I'm coming from, Chennai. This bridge is quite spectacular in terms of its location. It's a bit slow. See, whenever I teach a application-oriented subject to my students, I always speak about the pioneers of our country, because many of the time our students are not aware who are the pioneers in our country. Okay, but we should have faith that we do have several role models. In the Assam Rail Link project, the person who was in charge was Colonel Singh. There is a nice report by him, a complete story of the Assam Rail Link project. It's quite a vivid document of the full project, and it is available in the internet. And he got the help from John Gammon, who started the company called Gammon India Limited. And there is, from Gammon India, there is one person, V.N. Hegare, who is still there, who has written a wonderful article, Evolution of Precast Segmental Technology of Bridges. That means these are few names who were involved in this Assam Rail Link project. Another person, Sitaram Joshi, he was Gandhian in his philosophy. He used to wear that type of dress. But you can see this way back, right after independence. This is a copy from one advertisement of his company, which was making Prestress concrete bridges. See, at that time also we were aiming for Atmanirbhar Bharat. T.N. Subbarao from Gammon India was a pioneering person who has developed, who is associated with John Gammon, and he has been felicitated in Europe. And these are the wonderful bridges, Prestress bridges, which has been done by Gammon India. This is the Pamban Bridge, again done by Gammon India. This is the box girder, main section box girders, and these are the approach sections.
Is this a drawbridge? It's not a drawbridge.
No, no. The drawbridge is a separate one. Just right to this is the drawbridge. That is the steel bridge. That was even built much earlier. This was built around 1970s, I think 72, 73. Whereas the drawbridge was built around 1911 or 12. And the drawbridge again has been refurbished. Okay. Chandar Alim Chandni from Stoops, he has been felicitated by the FIB, the European Concrete Society. His company, the Stoops, have also been very much involved in Prestress concrete. Now this is an aqueduct, the Bhima aqueduct. This particular cross-section was an optimized section, and this is a very prestigious project in this water scarce area of Maharashtra, in the Vidarbha area. Mahesh Tandon today in fact Mahesh Tandon is in IIT Madras. He's speaking in the Institution of Bridge Engineers conference there. Mahesh Tandon was educated in the University of Hawaii, and his company, Tandon Consultants, did a lot of work on the viaducts, metro viaducts. Another person of his company, Vinay Gupta, he gives a lot of seminars. Okay. Okay. Coming to advantages of Prestress concrete. Why do we go for prestressing? The initial thought was that if we can have concrete to be uncracked under the service condition, then the durability improves. And definitely that's a big advantage, that due to its uncracked under service conditions, we can have increase in durability. This is something, as I said, our generation we are facing, that it is not that every time we will be constructing new stuff. You have to rehabilitate the existing stuff. Okay. If we can delay the need of rehabilitation, that is definitely better. And prestressing is beneficial in that. In terms of the design, full section. Full section is utilized in terms of section properties. We can use the uncracked moment of inertia, and it improves the deformations, and we also get benefit in shear capacity. If you are talking of any liquid retaining structures or even very high-end structures like nuclear containment structures, then definitely we go for what is called leak proofness, and there pre-stressing is beneficial. If you're talking of dynamic loads, repeated loads, like fatigue issues, we can go for pre-stressing, like railway sleepers. Second is the span to depth ratio. This is an architectural consideration. Whenever we are going for long span auditoriums, roofs, then pre-stressing is a solution. These are some typical numbers that for a non-pre-stressed slab, the span to depth will be around 28:1, whereas for pre-stressed slab, we can go for a much higher span to depth. And the corollary is that once we can go for a reduced depth, it leads to a reduction in the self-weight. For bridges, this is a factor, because in bridge design, you will see that the self-weight moment itself is substantially high, comparable to the live load moment. Now, if the self-weight moment can be reduced, then it is advantageous in terms of design. We can have an economical solution. However, what are the challenges? These challenges, we shall see the same challenges are there in precast also. Skill technology. See, now in our country, sometimes even our students think that what is there in concrete? You just mix something and pour something. But no, we have to go for very high quality products. Both pre-stressing and precast, they need skilled technology. Use of high strength materials is costly. Yes, if you are talking of ultra high performance concrete, we can solve many problems, but we also have to pay the price. Okay. There is additional cost in auxiliary equipments. For pre-stressing, if you are a contractor, you have to bring in those equipments, and we have to have the quality control and inspection. Same applies for precast, that in order to get the benefits, first you have to pay the price in terms of good inspection. Now, the types of pre-stressing, there are different ways of classifying. It can be how you are applying the pre-stressing force. Typically, we apply that by hydraulic jacks, but there are other ways of applying. External or internal. This is more used in bridges, that our ducts can be inside the section or the ducts can be outside the section. Outside the section does not mean that they are always visible. Like in a box girder, the ducts can be inside the box, but not within the section. And their analysis is slightly different compared to a duct which is inside the section. Now, this is the classification today which we will be talking about pre-tensioning or post-tensioning. I will come into that later. Linear or circular. For most of the linear members like girders or any slabs, these are, although the profile may be slightly curved, but we say it's a linear pre-stressing. Whereas if you are going for pre-stressing pipes or pre-stressing containment structures or pre-stressing domes, then these are circular pre-stressing. Full, limited or partial. Now, this classification is more of a design perspective. In the earlier days, the idea was that we shall have concrete uncracked under service condition. But then it was found, that is called full pre-stressing. But then it was found that that is uneconomical. Most of the time we do not have the characteristic load, and if you are targeting uncracked under characteristic load, then it is uneconomical. Hence we say that, okay, let it crack under the characteristic load, but most of the time we do not see the characteristic load. As per the definition of the characteristic load, only 5% of the time we may expect. Rest of the time the load may be much less, and whatever cracks may form in case if the characteristic load is there, that will get closed. That is called limited prestressing. That means we are relying on the prestressing to check cracking for most of the time, but need not be for the characteristic load. Okay. Partial prestressing is a very generic term. It means a mix of reinforced concrete and prestressed concrete. Full prestressed concrete is one end of a spectrum, and reinforced concrete is another end. Anywhere in between, a mix of reinforced concrete and prestressed concrete is partial prestressing. You can say that the prestressing is primarily for the dead load, whereas for the live load, I will take advantage of the reinforced concrete. Something like that. The way you select it is a very case-to-case basis. Uniaxial, biaxial, multi-axial. In a beam, we have prestressing only in one direction, whereas in a slab, we can have prestressing in two directions, and for a dome, we can have prestressing in like three directions. Okay, trying to quickly go through the process. Pre-tensioned is typically used for members which are produced in bulk. It is easier to produce smaller members in bulk like railway sleepers, but we can also have bridge girders which are being pre-tensioned. Okay. Now, in a railway sleeper, we will be having like a traveling stress bench. What is a stress bench? It is like a mold with, it's a self-straining frame, I would say, not a mold, self-straining frame which can move around on rails. First, inside this self-straining frame, there is a mold. We are putting the strands, we are anchoring the strands, then we are stretching the strands, and this can be monitored by some scale or some pressure gauge. Once we have stretched the strand, that's the pre-tensioning. Then we are pouring the concrete. We have a batching plant. Through a hopper, we are pouring the concrete, and then we are vibrating the whole mold itself, and then we are pushing this whole stress bench through the rails into the curing chamber, steam curing. We will be keeping there for about 24 hours. After 24 hours, they are brought out. The molds can be released because in a factory, we need the molds very quickly. And hence, they are cut, they are demolded, and then again they are water cured for maybe, 24 hours of curing is equivalent to almost 7 days of curing. That means for another 3 weeks, they will be curing separately in water tanks. And then they will be dispatched. Now this is a complete industrial process, and if you're in a railway sleeper factories, there are several of them in our country, and the first generation of pre-tensioned sleepers are now being again replaced. That means the industry will go on because this production these are also precast pre-stressed. And hence, this is a pretty, I would say, the railways, whichever factories I visited, they have their own specifications of testing these sleepers.
So these strands are made of which material?
What's that?
Strands.
Yes.
Are made of which material?
The strands are of high-strength steel, obviously, high-strength steel. Pre-stressing means we have to go for high-strength steel, minimum requirement. And also typical high-strength concrete. Minimum grade is meant, but harping is more efficient in terms of the number of strands that you can use. Okay. Next is the post-tension members. And here also the way I am talking about the post-tension is just with reference to precast. Okay. That post-tension can also be used in precast. Like this is a site which I went in Ernakulam. This is a post-tension box girder. Here you can see that the reinforcement has been fabricated, the ducts are placed, then this mold is taken to this casting yard. Once the concrete has been cast, then the strands are passed through the ducts, and then against the hardened concrete, the strands are stretched. That means here the concrete is cast first and then the strand is stretched. And this can be done in stages. That means a few strands are stretched in the site, then they are taken maybe through some floating cranes. This was in the construction of a bridge. And then at the site, at the final location, again some more strands can be stretched. Now this is the final form of the Goshri Bridge in Cochin, quite in a very picturesque location. And this was quite a prestigious project at the time the Cochin Port Trust had undertaken. Coming to other types of bridge girders, this is from the Chennai Metro Rail project. That these are the molds, the concrete is being cast, and then these are the anchorage blocks at the end, which are required to reduce the bearing stress which comes during the post-tensioning. Now, what are the advantages of post-tensioning as compared to pre-tensioning? If it's a very heavy member, then post-tensioning can be done right at the site itself. I do not need a factory to do post-tensioning. And in our country, in bridges, mostly they were post-tensioned earlier. Now, of course, we are seeing pre-tensioned girders coming in. There is a less waiting period in the casting bed. What it means is that we are not transferring the stress to the concrete as early as we do in pre-tension. Hence, once the concrete gets a minimum strength, it can be demolded. Transfer of prestress independent of transmission length. Here we have some physical anchorage at the end, anchor blocks, and hence we do not depend upon the bond to transfer the prestress. It is the anchor blocks which is transferring the prestress. Suitable for segmental construction. Now this is a technique which has become quite common for the viaduct construction. Can be applied to curved members. Pre-tension members cannot be used for horizontally curved members, whereas post-tension can be used. Now what are the relative disadvantages of post-tensioning? That we need ducts, we need anchorage device, and we need grouting. Now this is a very important aspect of post-tensioning. See, in pre-tension, the strands are in direct contact with the concrete. There is good transmission of bond, provided the concrete has been cured, and we can have some minimum, I would say, durability satisfied if the concrete is of good quality. Whereas in post-tension, there is a duct which is a void. Through that we are putting the strands, and then we are grouting it, and the grouting should be high strength, non-shrink. We expect the grout to fill up the full space, which itself is a challenge. And this grout, how much durable it is, that's the challenge. My colleague, Professor Radhakrishna Pillai, who did his PhD in University at Texas A&M, he studied these post-tension girders in US, and they found that the grout gets deteriorated. They did this UPV, ultrasonic pulse velocity test, and found that voids are there within that duct. This is a challenge, that if you are targeting a 100-year life for a bridge girder, especially the segmental construction, is the grouting done properly or not? See, in our country, we are in a hurry to have our infrastructure developed. But this is one area which future will say how well we have done it. Professor Radhakrishnan is very much passionate about talking about grouts. Okay. Now, what are the devices we need for post-tensioning? We need a casting bed. We do not need any pre-stressing bench as such, because we are doing the pre-stressing against the member. Of course, we need mold and shuttering. We need ducts. We need anchorage devices, very large anchorage devices. Jacks, couplers we may need if you are going for continuous members, and grouting equipment. Why I have written optional is, in a country like US, sometimes they do not go for grouting in the post-tension slabs, because they say it is an The slabs are building members which are in an interior environment. Let's get rid of the grouting. And by that, they're reducing the cost. In India, of course, the precasters, they don't take the risk. Even for post-tension slabs, they go for grouting.
So without grouting, there will be a gap between the concrete and the...
Yes. Then the analysis is different. The unbonded post-tensioning analysis is different compared to the bonded post-tension. That is one difference in the analysis. In terms of durability, you have to use special purpose strands which are encapsulated, and so that you can increase their longevity.
Okay. But when removing anchoring, it will again move to its previous state. No? If suppose there is no...
No, the anchoring has to be there.
Okay, sure.
Anchoring has to be there. Anchoring is there.
Okay, sure.
The anchoring device is already, it's there along with the member.
Okay, sure.
The nice thing of unbonded is, see, now these days, they are going for a mix of bonded and unbonded tendons. The reason is, unbonded tendons you can replace. And that is one nice aspect, that in future, if you suspect that you need to upgrade, okay, you keep some ducts free, extra ducts. There you can put some strands later on, or you can replace some of the unbonded strands and try to put new strands. This is also has been taken, especially if you are seeing these bridge girders, they will keep extra ducts in place for this only, because we are not sure how well they will perform, say 50 years down the road. We have a provision to strengthen them in future. Next is the losses in prestress. Now this, as I'm saying, that I'm trying to cover like a course in one lecture. The losses in prestress comes from different sources. We broadly classify the losses into two groups. One is called immediate loss. What is meant by loss? That whatever force we are recording during prestressing, over a period of time that force gets reduced in the strands as well as in the concrete. One set of loss happens during the prestressing itself, that is called immediate, and under the immediate we have elastic shortening. What is meant by elastic shortening? That in pre-tension members, whenever we are cutting the strands and by bond they're transferring the prestress in the concrete, there is a reduction in length. It's a physical phenomenon that the strand is trying to retract, the concrete is not allowing it to retract, but the concrete is getting compressed to a certain extent, and through that extent we are losing the increased in length of the strands, and that is called elastic shortening. Friction happens whenever we have a curved tendon, that it's like a belt friction type of situation, that whenever we are trying to stretch a strand against a curved duct, there will be a friction acting, and hence from the stretching end there will be a drop in prestress till the dead end. Anchorage slip is an issue which typically not of a concern of a bridge girder, but if it is a small members, it can be an issue. That whenever we are taking out the jack, and this is in pre-tension, this is in post-tension, and this is also in post-tension. In anchorage slip, whenever these wedges are trying to sit in the anchor blocks, there will be a certain reduction in length, and that leads to a drop in stress at the end region. Compared to the immediate losses, the more crucial are the time-dependent losses. Time-dependent losses are material phenomenon, and substantial amount of research goes in this time-dependent losses. Okay. The first is a creep. As I said, that this is the disadvantage of prestressed concrete, that we are having a permanent compression in the concrete. And concrete having voids, and voids also generate because of the evaporation of unused water, it compresses under this stress. And creep can be a major concern not just for concrete, for masonry and other types of material which are porous in nature. And with creep, the pre-stressing also gets reduced, because if the concrete is reducing in length under the stress, then the steel is also reducing, and hence the pre-stressing is dropping. Second is a shrinkage. The shrinkage is a phenomenon for concrete because of the cement hydration. There are two types of shrinkage. One is called autogenous shrinkage, another is called the plastic shrinkage. Autogenous shrinkage means that whenever you are curing the concrete, because of the hydration reaction, the concrete will try to reduce in length. Okay, that means in a post-tension member, the pre-tension member, before you are transferring the pre-stress, this autogenous shrinkage should happen so that is not counted as a loss. Whereas, after you have stopped curing, as it is drying, then there will be drying shrinkage. Now, which one will be more? It depends upon the type of concrete. Typically, for conventional concrete, autogenous shrinkage is less, the drying shrinkage is more, depending also upon the weather. If I take a place like Hyderabad doing the pre-stressing in the month of May, obviously the drying shrinkage will be quite high. Whereas for very high strength concrete, the autogenous shrinkage can be high and the drying shrinkage can be low if you are in a place where humidity is high. That means it's a matter of where you are doing, when you are doing, whether autogenous is more or whether the drying shrinkage is more, it depends. Typically, drying shrinkage is higher. Relaxation. Now, the relaxation loss is a phenomenon for the steel. That if you stretch a steel, the way we define relaxation is that in order to keep it in a stressed condition, the stress that I need gradually drops in order to keep it in its stressed condition. Okay. This drop also depends on the temperature. If it is a high temperature, like a nuclear reactor, where the temperature can go up to more than 45 degrees Celsius, this relaxation loss can be high. And hence, in that type of situation, we have to be concerned so that over a period of time, this relaxation loss is going to happen. The stress is going to drop in a certain, for a given strain, the drop in stress is the definition of relaxation. Okay, this is the write-up that the short-term immediate losses are a physical phenomenon, whereas the long-term time-dependent losses are the material phenomenon. Now, again, as I said, this is just 3 slides on losses, which I typically cover in at least a week or 2 weeks. Next comes the analysis. Now, this is important for this particular course. Okay. First, to understand the effect of pre-stressing on the stresses. See, a very important aspect of pre-stressed concrete is the computation of the stress. First, at the transfer. That at the transfer, the concrete is still not strong enough. It depends. The contractor will try to transfer the pre-stress as fast as possible to release the molds. But you as an engineer, you will say, no, please wait. Let the concrete mature properly. Then only you should transfer the pre-stress. The stress check this is for an axial member, like a railway sleeper. The stress in the concrete at transfer is the pre-stressing force that you are recording, that is P0, divided by the area of the concrete. The sign convention that I am using is for compression, it is being denoted as negative. Now this P0, there can be some short-term loss due to elastic shortening that you have to be careful. And this is the stress. First you have to make sure that it is within the allowable value of pre-stress for that particular age of concrete. That means if I am transferring the pre-stress after 24 hours, which is of steam curing, which is equivalent to 7 days of moist curing. That means whatever strength it is supposed to gain in 7 days, with respect to that, there is a permissible stress, and this particular stress has to be less than the permissible stress. Next comes the analysis at service loads. Under the service loads, the first term is similar to what we had seen earlier. Due to pre-stressing, there is a permanent stress. However, please note, now the pre-stressing force will gradually drop over a period of time. And hence from P0, we are now saying that at service condition, the stress is being denoted as PE, which is the effective pre-stress after a certain time. To this pre-compression, we are adding whatever stress is coming due to the external load. If the external load is tensile, then this is a positive sign. If the external load is compression, then it is a negative sign. Axially loaded members typically are members which are under tension, which can be like railway sleepers is one of them because the tension coming to the bending, or it can be ring members at the base of domes, or it can be some tie members. Okay, and hence this pre-stressing, this component will be typically positive. It's the tension which is coming, and in the denominator we have the transformed area, which is a more precise way of saying that now the steel is also participating along with the concrete to take tension. Okay. Now this stress should be less than whatever is the allowable value under service condition. Now if I say that I have a concrete tie which should not crack under service condition, that means this stress should be less than the cracking value, which is like a limited pre-stressing. But if I say, no, I will not allow the tie member to come under tension at all, then the resultant stress should be compressive. Okay, that means finally you are checking this stress against the allowable value which you are deciding a priori, whether it is a full pre-stressing, whether it is a limited pre-stressing, whether it is partial pre-stressing. Based on that, you have an allowable value, and against that you are comparing this. Now coming to the members under flexion. Okay. Now, why is the analysis important from the structural design point of view? First, right now we just say the permissible pre-stress based on allowable stresses at transfer. For pre-stress concrete, whether it is pre-tension or whether it is post-tension, whenever you are transferring the pre-stress, that itself is a critical time for the member. I have seen when I went to Coimbatore PSG Tech, one day I was just walking in the morning and they were jackhammering an overbridge across their road which goes in front of PSG Tech. And I said, what happened? It looks like a new construction. They said that during post-tensioning, this concrete cracked. And now the university management is saying that we will not accept it, you have to demolish it. That means the contractor had to demolish a newly constructed bridge which cracked during the post-tensioning. Hence, it is a very critical, it is easy to give a lecture in the room, but it is a difficult thing in practice because concrete can have weak spots, it can be variable throughout the length of the bridge, and hence we have to be very cautious that during the time of transfer, we are having sufficient material strength data to take a decision that whether we can transfer the pre-stress or not. Next, under the service conditions, there also we have to be, the stresses have to be under the allowable values. Why? Mostly it is because of the creep. Unless if they're not within the allowable values, concrete under compression will undergo creep. Okay. Concrete under tension may go from small tension to higher tension, which is not desirable. Hence, we have to check the allowable we have to make sure that the stresses under service loads are within the allowable value under service conditions. Now, please note, in a bridge, these checks are actually much more involved than just a one-line statement. If you're familiar with the code IRC 112, Indian Roads Congress Code 112, which is for the bridge, there are different types of load combinations: transient, rare, frequent, and based on that, there are different allowable stress conditions. Because, as I'm saying, that in a bridge, what happens is some of the loads may appear to be temporary, but they are there for quite some time, especially I would say, there are definitions at which load is considered to be frequent. But then there are loads like the class 70R vehicles, which are called rare loads. Okay, we don't have to worry about the rare loads, and hence the permissible stresses are raised for those rare combination of the loads. Hence, my point is, compared to buildings, if I am having bridges, then these checks are much more involved. In buildings, of course, it is relatively straightforward. Our service conditions typically are checked against the characteristic demand. Next, very important is to understand the behavior of a member. What is meant by behavior? Behavior means it is not just the strength a member is having, but if you're going on increasing the load, what is the deformation? How much it is going to bend? How much is the curvature? That gives an idea about what is called ductility. And I'm pretty sure Professor Sri will be talking about this much more, the behavior aspect. Strength is one. That is the primary requirement. That's the safety. But then the behavior issues are related with what is called ductility, which is a requirement for seismic design. Now, in order to get a behavior of a pre-stressed member like a bridge girder, first we have to understand the moment at decompression and cracking. That means, what is the load at which the bottom of the girder will have zero stress? That is called the point of decompression. That means any load more than that will create tension. Okay. We do not want the frequent loads to be more than that. Okay. Then what is the moment at cracking? That means any load which will be crossing the load corresponding to the moment at cracking will generate some trouble. Hence, we have to be aware what is the decompression moment, what is the cracking moment. This is the one aspect of behavior. Next is the strength. Strength, obviously we have to check. Strength is a one-time affair for a member. Means the characteristic load, as I said, that the definition is that the 95% of the time we do not expect the load to reach that value. But it may happen that within your service life, that characteristic load may come. In that case, civil engineering failures are very uncompromising. Okay, I tell, when I first entered civil engineering, my seniors of other disciplines, they said that you guys use a lot of safety factors, you don't know your subject properly, that's why you are using a lot of safety factors. I was young at that time, I couldn't reply, but now I tell my students, it's not like a cell phone that if it doesn't work, you just throw it away and get another one. Maybe it is an irritation if the cell phone doesn't work, but if it is not causing major disaster, whereas in civil engineering, whether it is structural, whether it is dam, whether it is something else, if there is a failure, it can be a major disaster. And hence, first what we look is the strength. And the strength, unfortunately, whatever is there during as built may not be there over a period of time. That's where the effect of corrosion comes in. And in a coastal region, India is having a huge coast, and also in industrial regions, we have a lot of corrosion issues. And what does corrosion affect? Corrosion primarily affects the strength. Okay, serviceability it may affect, but not to that extent. It's the strength which gets compromised. And finally, the entire load versus deformation behavior. The load versus deformation behavior can be studied first in terms of a section, that given a certain section, what is the moment versus curvature? Or you can also express it in terms of moment versus rotation, which is an integration of a curvature over a certain length. Okay, what is the moment versus rotation for this particular design section? Then we can go to a member level. What is the load versus deflection? Okay, that means the deflection again is an integrated effect of the curvature over the full length of the member. That is another way of viewing the behavior, load versus deflection. And if I am going to a building level, system level, then what is the, say, lateral load versus drift, which is an integrated effect of the full building system. And again, this will also come up in this course. Now here what I'm saying is that understanding the load versus deformation becomes necessary to understand ductility, to understand the overall system behavior. Now whenever we do the analysis, we have certain assumptions. Now I tell the students these assumptions may appear trivial, but you should know where these assumptions are not applicable. That's the most important thing. First is the plane sections remain plane till failure, which is known as the Bernoulli's hypothesis. But if I am going for deep members, then this assumption may not be true. The method of analysis that I am showing will not be true. Hence, you should be aware when not to use this plane sections remain plane. This gives this very important, I would say, quantitative information. The distribution of the flexural normal strain is linear across the depth of the section. This is from where we start our analysis of bending. When we study civil engineering in our second year, this is where we start from. The strain, the profile is linear. This is violated if the member is deep. Here we are talking about straight members with prismatic section and a vertical plane of symmetry. When is this violated? Today, if I am talking of a curved bridge girder, then this will not be true. Okay, there are other issues coming in. Prismatic section. For a bridge girder, we had seen these nice bridges, the Mahatma Gandhi Setu or the Pamban Bridge, that they are all nicely profiled. Okay, that means those are not prismatic sections. Again, there are certain issues if they are non-prismatic. Vertical plane of symmetry. For most of our civil engineering structures, concrete, our sections are symmetric about a vertical plane. But we can also have members like our structural steel, like C-sections can be there. In stadium construction, precast members can be non-symmetric about a vertical plane. And then there are additional issues which needs to be thought of. Some of this, in precast members, we face challenges similar to structural steel members like lateral torsional buckling, okay, while transporting the members. Okay, if the members are not symmetric, then these issues are more. Okay, now since the Prestress members are uncracked at transfer and under service for most of the time, we take advantage of that. What is the advantage? That's what we said earlier at the beginning, that both concrete and steel can be treated as linear elastic. What is meant by linear elastic? That the stress is proportional to the strain till the service loads. Okay, and once we have this assumption, then we can use what is called the principle of superposition. The principle of superposition means whatever is the deformation under a certain type of load and a deformation under a different type of load, they can be added together when the two loads are acting together. That's the meaning of the principle of superposition. But if you are going to the ultimate, then this principle of superposition is not valid. Another assumption is the increase in stress in the pre-stressing steel due to the bending is neglected. So whenever a member bends, the pre-stressing steel will slightly increase in length. But that increase in length is much less compared to the initial stretching. And hence, for convenience, we are saying that whatever pre-stressing is there due to the initial stretching, of course that will go on changing because of the losses, but we are not considering any increase due to the member deformation itself. In that way, our analysis remains simpler. Okay. Now, whenever we talk of analysis, primarily we are doing for two stages. First, at transfer, we had talked about under the axial loaded members. Now we are talking in the flexural members at transfer and then under service. But please note, for precast members, the intermediate stage, which is also called the transient stage, can also be very important. Okay, depending upon how large the members are, how long are you holding those members, how are you lifting the members, those intermediate stages can also be a consideration. Here, the analysis of transfer and the service are similar because they are based on linear elastic, and I'm just explaining only for one case under service loads. Given that yes.
Just one point I wanted to highlight.
Yes.
As you said correctly, the transient stage is very, very important. We went to a industry there. They manufactured a lot of these girders and they transferred the Prestress. It had a camber, but it was not seeing the dead load immediately. That means it was not erected at the site. It was kept for almost 2 years. Then the creep kicked in and the camber increased almost twice. So if it is, that's why the stages of loading is very important. And I was never seeing that the camber will go up that much. If it had seen the dead load, it would have been fine. But I just thought
yes,
to highlight
this is also a very important point that you cannot leave a member pre-stressed without loading it by the external load for a long time. Then this problem will come.
very surprising, just because it
I was not aware
the
of
load,
this, yes.
The camber went up.
Yeah.
It was kept for 2 years, huh? Without
Yeah. Because of the project, molding and materials.
As I'm saying that in real life, actually the challenges are not typical textbook problems. You don't know what type of challenges will come. Okay, like this, I was also not aware that it has been kept for 2 years and the camber is going on increasing. Okay. Now, whenever we are doing the analysis for transfer or service loads, we are invoking the linear elastic theory. And there are three approaches. This I am just referring as per the book by Lean and Burns. That's a very standard book which our previous generation has also studied, and I also teach from that book only. Very nicely explained in that book. The stress concept is the most important one because we need to check the stresses, whether at transfer, whether at service. Okay. And what is the purpose of checking the stresses? That they have to be within the allowable value, both at transfer as well as service, both for the compression side as well as the tension side. That means we have typically minimum 4 stress checks. At transfer, what is happening to the concrete in the compression side and the tension side. At service, what is happening to the concrete at the compression and the tension side. Please note, they get reversed. At transfer, as Professor Surya said, the tension comes at the top, compression at the bottom for a typical flexural member. Whereas at the service stage, it is the compression at the top and tension at the bottom. Okay. This is the very simple member, simply supported like a prismatic section with a strand which is at a constant eccentricity. In a flexural member, this is another governing variable. In design, we have to determine what is the pre-stressing force and also what is the eccentricity of this centroid of the pre-stressing steel with respect to the centroid of the concrete section. Now we are just explaining for this simple case for a member with a constant eccentricity, that we need to understand these stress diagrams. In fact, my teacher, Professor Belarbi, will not give marks unless you draw these stress diagrams, along with the values. That at a certain section, say the critical section at the middle, we have the prestressing force, we have the moment, which comes due to its own weight and the service load. Due to the prestressing force, first we have a compression, plus a variation of the compression due to the eccentricity of the prestressing force. So once I understand this, I can write the expressions very neatly. To that, this is what is there inside the member in an internal equilibrium. Then comes the external effect, including the weight of the member, which is creating a reversed type of situation, compression at the top and tension at the bottom. The resultant will be somewhat like this, which can have a net compression or it can be a tension if it is a limited prestressing. That is, this we have to, if I'm able to calculate properly, then itself, that's a proper approach that you should be able to understand these stress blocks. The expression for all this is given by this generic form. The first one is the uniform compression. Next one is the varying stress due to the eccentricity of the prestressing. And then the next one is the effect of the external, which is also including the self-weight. The combination of plus minus has to be selected appropriately, and then only you can get the resultant stress at the top and the resultant stress at the bottom. Please note, I have written this as a generic way. This can be used both at transfer as well as service, as well as for any intermediate stage. For a curved tendon, curved means it's curved in the vertical direction. P can be substituted by its horizontal component, which typically we neglected, that especially towards the end, if that tendon is highly curved, then theoretically we should take only the horizontal component of the prestressing force. But since in a bridge girder this curvature is very, I would say less, typically we disregard this effect of the horizontal component will be almost same as the total prestressing. Okay, with this, I am ending the first lecture on, today what I will do is, let me start the second one. Okay, I will be having a tutorial at the end.
Sure.
So that some of these ideas.
You can go another half an hour.
Yes.
Yeah.
What we went through is a quick brush up of the prestress concrete. We talked about the advantages. We should be aware of this whenever we are taking decisions, whenever we are doing some value engineering. Then the pre-tensioned and post-tensioned, the two cases, they have their own uniqueness in terms of the equipments that we need, the losses that we have, and the construction methodology. Then first we did the analysis under axial load, which is because that is easy to understand, whereas the most of the application is for a member under bending, which is where we have to talk about I just covered only one type, which is the analysis based on stress. What are the other two methods? The load analysis based on loads. That is used for a design of prestress members. But since this course is not covering prestress members in details, I did not cover that approach because I don't think we are going to design any prestress members here. Third concept is the load balancing concept that is used for the deflection computations. Okay, those two I just skipped. Okay, any question? Today at the end of the day, we will be doing a small tutorial problem so that you have some sort of comfortness that you are understanding these concepts. Okay.
So whether only conventional type of high strength concrete can be used, you told that only high strength concrete can be used. Whether we can go for fiber reinforced concrete?
Yeah. The special types of concrete, fiber reinforced concrete is becoming very common. I mean, even the UHPC is becoming very common. I would not say very. common in bridge girders because to reduce the effect of cracks. Yes.
In one of your studies, you talked about the cracking stage and then an ultimate stage. How are those two different? If there is a cracking stage, wouldn't the crack intercept the pre-stressing tendon and then it will ultimately lead to the ultimate stage at that
No, no, no. Can I use a chalk?
Yeah. You can use either side.
Yeah. No, I prefer chalk than this one. Okay. Now I'm going to my favorite topic. If I look into a reinforced concrete member, the moment versus curvature is linear till a certain stage. That is the cracking. Now once it cracks, there is a reorientation of the stresses. And now it follows a different trajectory and it becomes nonlinear. This is the basic moment versus curvature behavior for a reinforced concrete member. This is called the cracking moment. This is the cracking curvature. Somewhere the steel will start to yield. Now this yielding, whether it is gradual or whether it is sudden, depends upon the type of steel. Okay. This moment is called the moment of yielding, and the corresponding curvature is called the yield curvature. And finally, when the concrete starts to crush, this is the ultimate moment, and this is the ultimate curvature. Now, if I try to answer your question, cracking is here, whereas this is the strength. Now, as a designer, what we do is, first we need to check the strength. Because as I said that failure of civil engineering things can be disastrous. Strength has to be checked. Cracking and yielding, this is our serviceable regime. These are related with our durability and other deflection and all that stuff. Okay. In prestress concrete, this becomes important because we are trying to take advantage of prestressing to reduce durability. Hence, if it is cracking too early, like in a partial prestress member, then we have to be cautious whether the durability will become an issue or not. These are quite different stages. Now, this is what is for reinforced concrete. Now, when it comes to prestress concrete, in prestressed concrete, when we are for a flexural member, the way we are putting the strand with an eccentricity creates a camber or hogging. Hence, in absence of any external moment, including its weight, there is a negative curvature, means it's a hogging. Then, with increasing load, the cracking moment is much higher compared to a reinforced concrete member, equivalent reinforced concrete member. That's where we get the benefit that most of our service loads, if it is in this region, prestressed concrete is staying uncracked compared to a equivalent reinforced concrete which would have cracked. Now, after cracking, the behavior is becoming similar to reinforced concrete. And the way I am saying equivalent means as if the strength is same. And the benefit of, now, what is the benefit of prestressing? The benefit of prestressing is that the increase in the cracking moment although the strength may be same. That means in a bridge girder, finally you're targeting the strength to be same. Whether it is RCPC, the strength target is same. But if you're adopting Prestress concrete, then you get benefit in the service stage.
Does that mean that the tendons they are acting as a reinforcement after the cracking is cracking?
Yes. After the cracking, the strands will act like conventional reinforcement. The prestressing will be still there. The effect of prestressing is there. But please note, after cracking, the strands will start to yield because they are of small diameter. And hence the behavior becomes nonlinear quite fast compared to reinforced concrete. In reinforced concrete, we still have a linear behavior. That means yielding is the difference between cracking and yielding is large in reinforced concrete, whereas in prestressed concrete, the difference between cracking and yielding is very less. That margin is small.
Sir, when you are saying stress deflections in texture,
Yes.
sir, if the deflections are very high, is there any increment in stresses due to fetal target, only due to prestress?
Okay. Now, P delta effect is something which comes for a compression member. If I just look into like a pile, okay. Although the strands are distributed along the periphery, I am just denoting it as a single line. Okay, please note, in a pile, strands will be distributed along the periphery. I'll be talking about precast piles in my next presentation. Now, when it bends, the strand also bends along with it. And the compression and tension, they don't become eccentric. They still are collinear at any section. Hence, prestressing does not involve P delta effect. P delta effect comes from external effect. It can become of a concern for a prestress member because if you are going for smaller size, then yes, even the piles can buckle due to the external load, not due to the prestressing, but due to the external load, yes, it can buckle. P delta effect should be considered in a pretension member or in a prestress member for the external loads because the members can be slender. See, some of the things we have to see, as I said, that we can reduce the depth of the member for a prestress, but then we have to make sure that deflection is not compromised. Similarly, the P delta effect.
So actually, post-section is we are going to do a prestress. Post-section is we are going to do a grouting is a mandatory. And then concrete have one strength, that is it is high strength and the grouting material is a different material compared to the concrete. And then in that too we are embedding a steel tendons. So three different materials might be, let's say it is a concrete, it is a harder concrete. Once again fresh grouting we are doing, it's a fresh property. Probably there will be weak interface might be created between concrete too and grouting material.
See, what you said is right. See, from the structural point of view, from the structural design, we say that if the grout is of at least of the strength of the concrete, typically the grout will be higher strength. Provided the grouting has been done properly, the transfer of stress from the strand to the grout to the concrete, we say that it happens so that there is no slip. That means there is perfect bond. From the structures, we push this. But whereas materials people, they will say, no, no, no. The bond between strand and grout, and then from grout to concrete, may not be that good. That means from the material point of view, yes, there is a debate whether the bond is same as that in a pre-tension member, where there is a direct contact of concrete with the steel. It is not. We have the strand, grout, then duct, then concrete. But by testing wise, I would say, at least in the books, I haven't seen any specific mention whether we should reduce the bond strength for a post-tension member or not. I would say from the structural design, we can neglect any bond slip, provided the grouting is done properly.
One is Let's say once concrete is harder, if you put any fresh concrete, in between surface treatment is somewhere required, not as regular.
No, here it is a duct is there.
Okay, sir, that is the one.
Duct is corrugated. It's a corrugated duct, which is also adds to the bond. You will always see that the duct cross section that I'm just trying to show a duct schematic sketch that there are corrugations on the duct. Why are these corrugations provided outside, not inside? Inside we do not provide because to reduce friction, otherwise there will be more friction. Inside is smooth. Outside there is this corrugations, that is to improve the bond. That is a must.
Actually, precasters prefer metal ducts over the HDPE only because the bond is better.
Yes.
The HDPE will have issues.
Which is smooth pipes, you are saying?
Smooth pipes,
No,
but-
no, smooth pipes are not
Yeah,
recommended.
but nowadays there is a tendency even with the corrugations in HDPE also. But the good quality precasters, they always use metal ducts.
Metal
Though
ducts.
it's little cumbersome to
Yes.
handle.
And the duct size should not be too large. Please note.
Yeah.
If your duct size is too large, then obviously your amount of grout is more. And then there's issues of corrosion. That's why if you go into post-tension slabs, ducts are flat ducts, very small depth. Okay. Through that you have to pass the strands.
And also see this grout is a high strength grout and not shrink.
Yes.
So typically, the bond is much better. If you do it properly, of course.
Grout of the grout that we are using in Prestress. See, if you look into the 1343 code, the revision of 2012, the main chapter which was revised was the grouting. There was a lot of emphasis is being placed on the grouting. Okay.
Yeah, the major problem again, corrosion comes from grout only.
Yeah.
If you have a lot of chlorides in the grout itself, then you create passage for the corrosion.
So because there are issues which I'm not the right person to discuss. There is a bit of sedimentation, water in a curved duct, water tends to accumulate at the top. From there, the corrosion starts. Okay, then I'm just initiating the second topic and we will wind up at 12:30.
You can go maybe up to 12:45.
12:45.
So, there is a
Fine.
small delay in lunch.
Fine, fine.